DuckDB under the hood, Module 4. When DuckDB reads 60 million rows from disk, those bytes don't vanish after the query finishes. They stay in RAM, in a structure called the buffer pool. The next query that touches the same data reads from RAM, not disk. 10 times faster on spinning drives, sometimes 20. But cap that RAM below what the query needs, and DuckDB spills intermediate data to disk. That's this module. DuckDB under the hood, Module 04, Memory and the Buffer Pool. The buffer pool keeps pages warm. The cold path is the first read. Data moves from disk to the buffer pool in RAM, then to the CPU. The warm path is for subsequent reads. Data goes from the buffer pool in RAM straight to the CPU. There is no disk I/O on the warm path. Pages are pinned in RAM after the first read. The default limit for the buffer pool is 80% of available memory. The same data is available without a second disk read. The DuckDB memory function gives you insight into DuckDB's memory usage. You can see what's in the memory pool. Memory usage. Bytes represents the bytes currently held in random access memory. Temporary storage. Bytes represents the bytes spilled to disk. A value of 0 means no spill. If temporary storage bytes is greater than 0, the query spilled to disk. This is an important rule to remember when optimizing queries. Let's walk through a demonstration of attaching to a container. Here we query the DuckDB memory table. We select the tag and memory usage in bytes. We filter for rows where memory usage is greater than 0. This shows the memory allocated by DuckDB itself. Here you see a simple query. It selects the order key. You can query DuckDB's memory usage with the DuckDB memory function. This query selects the tag and memory usage in bytes. It filters for allocations greater than 0 bytes. The results are ordered by memory usage in descending order. This shows the memory breakdown after the buffer fill. You see the buffer manager using a large amount of memory. In the next clip, you'll see how to set a memory limit. Now, let's detach, reattach fresh, and cap memory at 64 megabytes, about 6 times smaller than what the full buffer needed. 61 megabytes. DuckDB rounds the limit to a power of 2 internally. Simple queries process one vector at a time, roughly 2,000 rows per batch. DuckDB reads a batch, processes it, discards it, reads the next. No accumulation. So no matter how many rows the table has, the working set stays tiny. Here, you see the query select L quantity, 10 from lenitum. This query multiplies each L quantity value by 10. The result is a stream of numbers. Next, you'll see how to group and aggregate these values. 73 milliseconds. Ungrouped aggregation uses one accumulator, a single running total, even less memory than the projection. Grouped aggregation is different. To count distinct values of L order key, DuckDB builds a hash table, one entry per distinct key. With 15 million distinct L order key values, that hash table needs hundreds of megabytes. 2 seconds, more than 3 times slower than without the memory limit. DuckDB had to spill, the hash table didn't fit in 64 megabytes. Here you can see the memory used by DuckDB. This query selects the tag, memory usage in bytes, and temporary storage in bytes. It filters for entries where either memory usage or temporary storage is greater than 0. This shows the memory used by different parts of the system. You'll see how this changes as we reset the configuration in the next step. You can reset a configuration setting to its default value. Here you reset memory limit to its default. It's time to put your knowledge into practice. Your exercise is to build your own buffer experiment. You can use the tools we've discussed to observe the effects of buffering. Try adjusting the buffer size and see how it impacts query performance. Experiment with different workloads to understand how buffering behaves under various conditions. This hands-on experience will solidify your understanding of how buffers work in DuckDB. Here is the solution. We use explain to reveal which plan operator each query uses. That determines whether spilling happens. First, sum of L quantity, no group by. The scan at the bottom reads L quantity from 60 million lenitum rows. Above it is the ungrouped aggregate operator. No group by means no key column. DuckDB maintains a single running accumulator. The working set is one 2,000 row input vector plus one counter. Memory usage is constant regardless of table size. This query never builds a hash table and never spills. Now, the group by query. Same 60 million rows, but DuckDB must track a count for every distinct order key. The scan reads L order key from lenitum, 60 million rows, roughly 15 million distinct keys. Above it is the hash group by operator. DuckDB allocates one hash table slot per distinct key. With roughly 15 million distinct order keys and 45 bits per slot, the hash table reaches about 84 megabytes. At a 64 megabyte memory limit, the table cannot fit. DuckDB spills hash partitions to disk and merges on the way back. The query finishes correctly, but slower than the streaming case. Let's land this. DuckDB caches table pages in a buffer pool. After the first read, subsequent queries on the same data read from RAM, no disk. Check the pool state live with DuckDB memory. Simple queries stream vector by vector, a 2000 row batch at a time, so they fit in even tight memory limits. Grouped aggregations with many distinct keys need a hash table proportional to the key count. When that hash table won't fit in RAM, DuckDB spills the overflow to a temporary file on disk. The query finishes, just slower. Two things to remember. Memory limit controls how much RAM DuckDB can use. Temporary storage bytes in DuckDB memory tells you whether you pushed past it.